Okay, this is my one slide summary of Kines 300, at least the most relevant element of Kines 300 as it applies to sport biomechanics. Sport biomechanics, I would define as the motion of athletes' bodies and the forces causing those motions. And I'll give you an example here of what I'm talking about there. Here, hopefully you guys can see this video playing in my video. Here is a video taken from a sprinting athlete training on the coolest lab in the world. This is a lab in Japan where they have 50 consecutive meters of force platforms. If you've been down in our lab in the SPH building here on campus, we have 10 force plates in a row, which is 20 feet of force plates, which is ballpark like 6 meters. And that's an awful lot. That's a pretty long stretch of force plates. You won't find too many labs in the United States, at least on college campuses, that have 6 consecutive meters of force plates. And this is a lab that has 50 consecutive meters of force plates. So you can study long motions like this, like extended maximum effort sprinting motions. And let me play that again. And while the athlete is running here, you see these pink lines coming up out of the ground when their feet are on the ground. Those are his ground reaction forces, the forces that he is generating under his feet when he's running. And if you sum those forces with gravity, you get the sum of the forces acting on his body mass here, m, and those forces sum to his body mass, m, times his acceleration, a. Okay? So by measuring those forces and by knowing his body mass, I could calculate his acceleration. And if I know those forces measured as a function of time throughout this whole time while he's sprinting across here, then I can calculate acceleration as a function of time. I can integrate that acceleration to get his velocity, and I can integrate his velocity to get his position. Okay? So these forces that he applies under his feet will directly influence, and one could even say dictate, the motion of his body, of his center of mass, his velocity, and his position across the track here while he's running. Now, especially if we're just dealing with, say, a point mass, it's actually a fairly simple task, fairly simple graduate level task, to calculate what are the forces under the feet that accelerate the body mass optimally to travel, in this case 50 meters, but extend this to like a 100-meter race, 100 meters as quickly as possible, in context of racing. That's a nice sport biomechanics problem there. What are the best ground reaction forces under the feet to accelerate my body as fast as possible or as best as possible to minimize the amount of time it takes me to travel 100 meters or to travel any particular distance. For a simple point mass, if I just represent the body as a single mass, assigned all of the body's mass as a point in space, that's actually a fairly simple problem to solve mathematically. It's in a field known as optimal control for the engineers in there. And for a point mass, that's a fairly simple task. But the body's not a point mass, right? The body is much more complicated than a single point mass with all the body's mass applied to it. It has joints, it has segments, it has muscles, it has ligaments, it has cartilage. It has lots of elements of complexity here that make it so that I can't just produce any old arbitrary force, I can only produce certain forces. So the more complicated task here in sport biomechanics is more along the lines of, given the confines and given the constraints of an athlete's body and an athlete's capabilities, what's the best way to move to generate the forces that are best or that are optimal for moving the athlete's body in such a way that they accomplish the best performance, that they maximize performance, such as in sprinting, maximizing average speed. Okay, so that's kind of the core question here in sport biomechanics and the core application of mechanics to sport biomechanics. What's the best way to move to best accomplish a certain performance goal, typically maximizing something or minimizing something? What's the best way to generate forces, or how can I train to allow my body to generate the best forces to accomplish a certain motion with the highest level of performance? And I'll give you a couple examples here of an exceptional performer here, Mr. Usain Bolt, who is pretty much indisputably the best sprinter of all time. And we'll see one of his most impressive performances here. This was the final of the 2008 Olympics in Beijing, China, when he won his first gold medal, 100-meter dash. Let's see a video here. So that is still today the most impressive thing that I've ever seen an athlete do, certainly in the Olympics. Maybe not in all things in sports, but certainly in the Olympics. He got off to a bad start. Bolt was not known for his good starts. He was relatively slow out of the blocks for somebody that's as fast as he is. He pulled up and slowed up to celebrate and stretched out his arm to beat his chest with like 10 meters still to go, and still ran 9.69 seconds, which established the world record at the time, and then, of course, won an Olympic gold. And so when he did that, everybody was kind of like, you just demolished the world record, and you didn't even try as hard as you possibly could. What's going to happen when this guy actually runs 100 meters as hard as you can? And here's what happens when he did that about a year later in the World Championships in Berlin. So he ran. Oh. So he ran 9.58 seconds there when he was actually trying for the entire race. Knocked off a good tenth of a second, a little bit more than a tenth of a second off his own world record, and that was 2009, and is still the world record today. And I don't think it's too controversial to say it's unlikely, I think, in at least our lifetimes that anybody is going to sniff that record. That's just really a performance for the ages. This is an incredibly impressive performance. Keep in mind here, he's competing against the other best sprinters in the world here. And after the first couple steps, keep an eye on Bolt here in lane 4 there, and watch him just in comparison to his position compared to the other athletes, and watch how just every step he, after the initial start here, he just keeps pulling further and further away in front of them. So just every step you can see him just getting further and further ahead. So a pretty impressive athlete. Now, what is it that makes him so good? There's a lot of things that are unique and different about Usain Bolt that you don't see in a lot of world-class level sprinters. In particular, he's very, very large, not necessarily like large and thick and heavy, but very large in terms of height and overall stature and leg length for a sprinter. Is that why he's so fast? And what is it about that makes him so fast? Here is just kind of for fun, but also for an illustrative purpose about what might make him so fast. Here it was him in 2009. Before this was actually 2017. Sorry, so this was right before Bolt retired for the first time, and here he is racing in kind of a jokey fashion. Bolt here actually raced about 120 meters, and the guy he's racing only had to run 100 meters, and we'll see the result here. So there's Bolt, the tall guy, and the person he's racing, the short guy. And then again, you can see him just eating up ground there on that person that he's competing against. Now, who was he competing against here? You might think, well, it's some nobody. The guy that he was competing against here was a fella named John Stephenson, who was actually in the 2004 Olympics for Australia and was a member of the silver medal winning 4x400 meter relay team in 2004 for Australia. And he had a personal best in the 200 meters of like 20.8 seconds or something like that. So he himself is a world-class sprinter. He was like, I think 7 or 8 years into retirement at the time when this video was taken, and Bolt was in the last year of his professional career before he retired. He was having some injury problems at the time, and certainly wasn't at his best, but was still pretty indisputably certainly one of the best, if not the best, sprinters in the world. So it's not quite necessarily an apples to apples comparison, but you can see here, just even in comparison to another world-class athlete, he's just moving in a very different way. He's just a very different shape of a body and a very unique look to his movement. And what we'd like to figure out in sport biomechanics is beyond just those qualitative statements that I made there, well, his body's different, well, his gait is different. What is it in terms of numbers that I can attach to his body that explains why he's so fast? What is it in terms of numbers that I can attach to describe the mechanics of his gait that makes him so fast? And in terms of projects in this class, this would be a great project or a topic for somebody to do for their project. What is it mechanically and structurally and anatomically about him that made him so fast? Why was he such an impressive athlete from a biomechanics perspective? My guess here, and where I would start if I was going to answer that question, and it would help if I could have found a slow motion version of this video. I couldn't, so we'll just watch it here again several times in fast speed. But you can see just how much ground he eats up with each stride that he takes there. Watch the rate of cycling of his legs compared to this guy's legs, and it's about the same, right? It's not like Usain Bolt's legs are just blurring by Roadrunner style. So he's not fast because he has superhuman ability to cycle his legs. He's fast because he takes enormous lengths of strides and just eats up a tremendous amount of ground with each stride that he takes. At least that's what I think, and that's where I would start if I was going to answer that question. Another example here of how long stride length can help you. This is another Jamaican athlete, Grace Jackson, who at least for female sprinters has the longest stride length on measure among female Olympic sprinting athletes. This was in the 1988, I think, 200-meter Olympic final, where she, I think, finished in second place. And you can see here just how enormously long her stride length is here, probably owing to her very long legs there. So it seems like the key to running fast in terms of sprints might be to have a long stride length. So just try to take as long a steps as you possibly can, right? Well, maybe it's not quite that simple, right? These athletes are very strong and very highly trained, and maybe it's something about their muscles or the properties of their muscles that's unique to them and allows them to produce the forces in the muscles and the moments at the joints to rotate the joints in the way that allows them to achieve such tremendous stride lengths. If I tried to use their stride lengths, being somebody with a different stature and with different muscular properties, I might actually be a little bit slower. So taking lessons from these elite athletes and applying them to lesser athletes and less gifted, less talented, less well-trained athletes may not necessarily always be the way to go. But we can certainly learn from looking at them about some general characteristics that might be beneficial mechanically for a high level of performance. Okay, another example of where stride length can make a big difference and can explain a very impressive sprinting performance, and this will be something we'll circle back to towards the end of class in the comparative section. The top speed that Usain Bolt reaches in his fastest race, which is typically the 200-meter dash, was a little bit under 30 miles per hour. So imagine driving your car down the road at 30 miles per hour, and if you just look out the window and see the road zipping by, imagine traveling like that on foot under your own power. That's the speed that Usain Bolt would briefly reach for his top speed in his 200-meter dash. A cheetah, on the other hand, is pretty much indisputably the best sprinter on Earth. Cheetahs can sustain top speeds briefly of up to 70 miles per hour. That'd be a full-grown, very fit, very healthy adult male cheetah can reach about 70 miles per hour and sustain that speed for a few seconds. They can travel from a dead stop at 0 miles per hour up to a speed of 60 miles per hour. Can accelerate from 0 to 60 in about 3 seconds. I don't know about you guys' car, but that's a heck of a lot faster than my car. And how do they do that exactly? Well, there's a lot of different scales of investigation we could look at there. We could look at the structure of the cheetah's body. We could look at the properties of their muscles. But if we consider speed as the product of stride length and stride frequency, we can look at the cheetah here and we can say, well, they're cycling their legs at a pretty normal rate there, right? If you count how quickly they're doing strides there, it's roughly similar to what an elite human sprinter might do, yet the cheetah is running 2 to 3 times faster than any human could hope to sustain. So if their stride frequency is normal and their speed is tremendous, then this must mean that their stride length is tremendous. And this is indeed how cheetahs attain their tremendous speed. They have actually surprisingly normal properties of their muscles in terms of fast twitch, fibers, and ability to produce muscular power and stuff like that. but because of the shape of the body and the flexibility of their spine, with each stride, they're able to cover a tremendous amount of distance and have an enormous stride length. And that's where their speed comes from, not from their ability to cycle their legs at a superhuman rate. They don't actually cycle their legs at a superhuman rate. So, using elements of mechanics and biomechanics to explain elite sprinting performance in the human realm and also in the animal kingdom.